Look up at the night sky, and the cosmos feels solid. We naturally assume this massive architecture is permanent. But every piece of matter out there is governed by a strict, inescapable rule. It always strives to reach its most stable state. Think of a ball at the top of a hill. It holds massive potential energy, making its position highly unstable. Give it a tiny push, and it rolls down, shedding energy until hitting flat ground. The energy zeroes out. The ball is at rest. We feel safe because we assume our universe has finished rolling. We take it for granted that reality has settled into its lowest, safest possible energy state. But we have to ask a critical question. What if the universe hasn't actually reached the bottom yet? Physicists call this a false vacuum. If we zoom out, we might find that reality is only paused on a temporary ledge, with a massive vertical drop waiting right beneath it. From our tiny vantage point resting on that ledge, the ground looks perfectly flat. We have no way of seeing the precipice. The universe we rely on might be a precarious trap, holding its position right up until the moment it suddenly falls. To understand how that drop happens, we have to look past the world of planets and gravity and zoom into the microscopic scale. Here, reality is built on quantum fields. You can think of these fields as invisible, fundamental grids that stretch across the entire cosmos, acting as the foundational fabric of everything. These grids follow the exact same rule as the ball on the hill. They strive to shed their potential energy and reach their lowest, most stable resting point. Most of them have, but there is one crucial grid acting differently, the Higgs field. This chart shows the energy levels of various quantum fields. Notice how the standard fields rest peacefully right at the zero baseline. Then look at the Higgs field. It hovers rigidly above zero, holding on to a reserve of latent energy. The Higgs field is stuck on the ledge. It represents a hidden flaw built directly into the architecture of reality. Because it holds this excess energy, the Higgs field is highly volatile. Imagine a piece of cloth soaking wet with gasoline. The fuel is already there. All it requires is a single random quantum disturbance, a tiny spark to disrupt the field. That spark pushes the Higgs field off its temporary ledge. It immediately plummets toward its true lowest stable state. The immediate reaction to this drop is the spontaneous creation of a bubble. Inside this sphere, reality has finally found its true ground state. This bubble expands outward in all directions, rapidly accelerating until it hits the speed of light. As the bubble expands, it alters the Higgs field itself, instantly rewriting the laws of physics and deleting every particle of matter in its path. A destructive event traveling at the universe's ultimate speed limit creates a terrifying mechanical reality. You would get exactly zero warning. The light carrying the visual information of the approaching bubble arrives at your eyes at the same fraction of a second as the destruction itself. You wouldn't see it coming. One moment you are looking at a vibrant sky, and the next you are simply erased. The death of the universe via Higgs field decay would not be a dramatic cataclysm. It would be a silent, instantaneous erasure of existence. But before you start to worry about impending doom, take a breath. This expanding bubble is currently a mathematical hypothesis. It is a theoretical possibility drawn from equations, not an observed certainty or an impending timeline. Modern science still has vast gaps in understanding particle physics and the nature of quantum fields. These terrifying models aren't reasons for despair. They are evidence that we are pushing into a thrilling, uncharted scientific frontier. Our universe is mathematically terrifying to us, but the fact that we can deduce the exact mechanics of its potential destruction means we have finally begun to decode the foundational language of the cosmos.